Dr. Saurav Chakrabarty, working as an associate professor in the computer science group at the Chennai Mathematical Institute, Tamil Nadu. Before joining Chennai Mathematical Institute, he was a postdoctorate at the Algorithms and Complexity Department of CWI, Amsterdam, Netherlands. He was a postdoctorate at the Computer Science Department of Technion, Israel. He was awarded PhD in Computer Science from University of Chicago. His area of research is theoretical computer science. His focus has been in the classical and quantum complexity of Boolean functions, including property testing, sensitivity, block sensitivity of Boolean functions, and quantum database search in electronic commerce, in graph algorithms, and in coding theory. He has published several research papers in both national and international journals.
Welcome to the UGC lecture series in computer science, and the topic is algorithms. So, today we will be looking at all pair shortest path, and we will be studying a particular algorithm known as the repeated squaring algorithm. So, that just to recap, we have a graph G which has n vertices and m edges. For example, here is a graph which has a certain number of edge weights, and the graph can be directed and there can be weights assigned to these edges, and we are interested in looking at the distance between two vertices. So, usually the distance between two vertices is defined as, in the case of unweighted graphs, as the number of edges in the path, and the distance between two vertices is its length of the shortest path from u to v. The problems that one asks typically are, what is the shortest distance from a vertex u to vertex v, and the second one is, what is the shortest distance of any vertex from the vertex v. And as we have seen that these two questions can be answered using the BFS algorithm. We can have also a more complicated one, where we can have weights assigned to each edges, and the length of a path is defined as the sum of the weights of on the edges in their path, and the shortest distance from u to v is the length of the shortest path from u to v. So, for example, here we have this graph and we have this path which is length 29, we have one more edge which has length 23, and there is one length which has one path which has length 22, and so on. Although the weights can also be negative, for example, here we can have the usual one, but we can also have a smaller length of length 9 that uses a negative weight. We also saw that there can be cycles. For example, this is a cycle, negative weight cycle of length 2 minus 2, and in this case one can get a distance from the G to A to be minus infinity. So, usually in the case of single source shortest path, you have been given the graph G, we have an edge weight. So, we have a weight assigned to every edge to a real number that can be positive or negative, and we have been given this source which is called S, and we want to output the shortest distance from S to all the vertices. So, in the 2 lectures ago we saw that there is a Dijkstra's algorithm that can find the shortest distance from u to v in order v squared steps, and it can also find the shortest distance from u to any vertex in v cube steps. But the catch is that this algorithm works only for positive weights, and a natural question to ask was, how can we handle negative weights, and we were looking at this dynamic programming algorithm. So, as we told last lecture, dynamic programming is a very essential and very important way of solving problems, and basically the idea is this, that you decompose the dynamic main problem into smaller problems, solve each of the smaller problems and store the result of the smaller problems in a table, and then use their results, combine them in a clever way to obtain the solution of the main problem. So, let us quickly go over the algorithm that we had done last time. So, again we have this graph and we have edge weights which can be negative, and the goal is to find the length of the shortest path from S to V. Now, what we define is that we define a new function called DLV, which stores the length of the shortest path from S to V using at most L edges. Now, this is a kind of a sub problem that we are talking about in case of dynamic programming. Now, the sub problems, it is like this kind of induction. What is the base case? Now, the base case here say if L equals to 1, meaning what is the length of the path from S to V using only one edge. Clearly, that can be done only when the vertex V is in the neighborhood of S, and in that case we define that the distance as WSV, the edge weight. And if V is not in the neighborhood of S, that means there is no edge from S to V. So, there is no way I can reach from S to V using just one edge. In that case, the distance is defined as infinity, and this is what is known as the head of the dynamic programming. So, it is important because this is one that tells us how to progress. So, the defining the DLV carefully is very important. We will see another example of dynamic programming where we will define a different kind of function. But once we define this function, we have to somehow understand how can we get the answers of this function from its smaller function. So, here it is the answer here that dl plus 1 v, meaning the shortest distance from S to V using L plus 1 steps, can either be one of this following. It can either be the shortest path of length L from S to V, or it can be the shortest path of length L from S to some other vertex u, and then taking one more edge from u to V. So, you minimize over all such u's in the intermediates. Clearly, this is right, because if you have a shortest path from S to V, then there must be a shortest path from S to some vertex L using one less edge. So, once you have defined this kind of a relationship, we can go ahead and start working on the problem. So, here we had done this one. So, say we have this graph G and we want to find the shortest path. So, we start with G is our starting vertex S. We first write down the case of 0. What are the distance of G to any of these vertices using 0 steps, and since 0 step nobody can go anywhere except for itself. So, only G has value 0 and the rest of them has value infinity. Now, come the next step where I come the second stage, meaning here it is 1. This computes the length of the shortest path from G to any of these vertices C or D or E using just one edge. Note that we can get this answered by the same recurrences. For example, say here we have it that this says that the shortest distance, shortest path from G to E using one edge is G to E is 9. Shortest path from G to V F is 11. Now, when we are looking at the second thing, what do we have? What is the shortest path from G to say A using 2 steps? Now, how can we find out? Of course, right now it can be infinity, or the other thing is that is there a way of going through something else? As you see that there is no way of going through something else, because G to something is not a neighbor of A. So, they will not get it. But for example, say B, what is the shortest path of length path from G to B? Now, right now infinity claims that there is no path from G to B using length 2, but we can have a path of length 1 say to G to F, but from F to B I do not know how to go. So, no good. But G to E I can go with a length 9, and from E to B I can go with a length 7. So, this will say that now I have a path of length 16 from G to B, and note that this is the best because I can minimize over all possible such paths, and so I can write here 16. Similarly, for C, you can see that this can become shortest path of length G to C right now of length 2 is going through E, and which will be 10, and from G to D will be, so either you can go for 9 plus 5 because 9 is there, and I can go for one more step 5, or I can go 11 plus 4, and 11 plus 4 is 15, 9 plus 5 is 14. So, this will be 14. Now, look at E. This is a very interesting thing. to go from G to E, I can either go in just one step, which in that case I will get 9, or I can go through something else, say F. I can go to F. Now, going to F using one step is 11. From F to E, I can go using -8. So, we can go from G to E using 11 plus -8, 3 or 9. So, we take the minimum of those and we will get 3 here, and similarly for F, we will not get any updates. So, this will be what we will be getting, and we can see that we get something like this. Again, say repeat here, say just consider the C setting. Right now, this table says that the shortest path from G to C is 10, basically via E. Now, when I am looking the next stage, which is shortest path from G to C using 3 edges, either I can go to from G to C using 2 edges, which is 10 is the best, or I can go from G to something else using 2 edges. For example, I can go from G to E using 2 edges, and then go from the edge E to C. Now, from going from shortest path of length G to E using 2 edges is now 3. So, I can go now from G to C using 3 plus 1, that is 4 edges, and so 4 and 10 we will write a 4 here, because 4 and 10, 4 is minimum. So, again we can keep on doing this one and we get this, and you can keep on doing this whole process one by one for every level, and at the end we will get to see that what is the shortest path from G to any vertex. So, in this case say we will get 4, 5 and 6. Note that there are only 7 edge vertices here. So, the shortest path from G to anything will take only 6 edges at the best, and this will give me the final output. It basically says the shortest path from G to A is 13. I do not even know which table is coming out like this. So, we have to cleverly find out which is the path that will go, and so on. So, there will be 3 here, 5 here and 5 here, but somehow the algorithm has found it out. All I have done is I filled up this table carefully. More importantly, say shortest path to 8 is 6. Now, how can it be 6? It cannot be 6, right? 9 plus 7 is 16, but it is there is a path. It is 11 minus 8. So, 3 plus 5 is 8, 8 plus 5 is 13, 13 minus 7 is 6. So, a very convoluted path will find it out, but the algorithm manages to do it. So, dynamic programming works like this. Good thing is that we have this table. How many vertices, how many places are there in this table? We have v square places in this table. Each place takes order v steps to find out, to fill up, because we have to take the minimum over all u, and thus it will require us order v cube steps. So, this gives us the single source shortest path problem. Dijkstra's algorithm orders for v square and Bellman-Ford works for v cube. We take a short break now. When we come back, we will see how to generalize this algorithm to finding out all pairs shortest path. Welcome back after the break. Before the break, we looked at the Bellman-Ford algorithm for the finding the shortest path from S to any vertices. Now, there is one more generalization that one can do, is that given a graph G, and for now say let us assume that the graphs can be edge weights, which can be positive or negative, and I want to find out the shortest path between any pair of vertex u v. So, earlier we had one source S and we wanted to find out the shortest path from S to any vertex, but now we are tracking out for all vertex u v pair what is the shortest path. It is something exactly like you have a map, and at any point of time I can ask that map what is the shortest path from point A to point B or point C to point D or something like that, and you should be able to give me the answer. So, you should have to compute the shortest path from any 2 points, and you do it quickly. So, how can we do? Of course, what we can do is that first idea is to do a Dijkstra. So, Dijkstra of course gives you the shortest path from any vertex from S. Now, I can change this S. So, for every vertex v, in the edge, vertex set, we can start a Dijkstra starting at that vertex V. And when we do that, we will get the shortest path from between any two pairs of vertices. The idea is simple, but let us try to understand what is the running time of this algorithm. Note that the Dijkstra for single source shortest path would take order V square steps. Now, I am running Dijkstra at all the possible vertices. So, the total number of steps required for solving the all pair shortest path using Dijkstra will be V cube. That is not such a bad algorithm. In order V cube, you get all the possible distances between any pairs of vertices. But again same catch exists, this works only for positive weights. For negative weights, one can say that we can do the same thing, we can do the Bellman-Ford algorithm from every possible other vertex. And again what we will have is that Bellman-Ford was taking V cube steps. So, using Bellman-Ford from all the algorithms takes order V square steps. So, thus either we can use Dijkstra and get an all pair shortest path algorithm in order V cube steps, but in the case of positive weights, and for negative weights I can use Bellman-Ford which does order V square steps. Now, question is that can one do better, and the idea is they can be done better and we use very clever dynamic programming. So, let us see again what is the dynamic programming. To repeat it again, we have to break it down into small problems, carefully define the small problems, solve these small problems, save them in a table and combine the solutions of the small problems to obtain the solution of the bigger problem. So, thus say for example, here we define it this way. Let us dl u v is the length of the shortest path from u to v using 2 to the power l edges. Now, one might ask why did we define 2 to the power l edges? You will only understand it when we finish this algorithm or define or look at how this can be generalized. But clearly, how did one come up with this definition is something one needs to think about, and definition is in fact the hardest part in this technique of dynamic programming. So, recall that in the earlier algorithm of Bellman-Ford, we had defined something called DLV, which was the length of the shortest path from u to from S to u and S to v using L edges. But now we have gone for 2 to the power L edges between any two pairs. Now, 2 to the power 0 is 1. So, d0 u v means what is the shortest path from going from u to v using one edge. Now, that is easy. You can go from u to v using one edge if and only if u v is an edge. So, in that case you can go with the path w u v, the edge weight, and if it is not in the edge set, then you cannot go from u to v, and in which case the algorithm will take distance of the path from u to v using one weight is minus infinity, or d0 u v is minus infinity. But this is where the interesting step lies again. How do we combine the sub problems? So, before we look at it, let us try to understand it in a slightly different way. Say I have a vertex here u and I have a vertex here v. I want to find out the shortest path of length say 16 from u to v. How can we do it? Now, this can happen if there exists a vertex here called w such that there is a path of length u of length less than or equals to 8 to w and a path from length w to v of length 8 less than 8. So, if both of them are less than 8, then the total path from u to v will be less than 16. This is what we use, that dl u v, the shortest path of length 2 to the power l, is we can get by you pick up a vertex w in v, it does not matter which w you choose, you find out the shortest path from u to w 2 to the power l minus 1 step or 2 to the power l by 2 steps, and then the shortest path from w to v again using 2 to the power l minus 1 step. So, combining these two we will get shortest path of length 2 to the power l from u to v. So, as we told, this is known as the head of the dynamic programming. So, abstractly thinking, in dynamic programming the hardest part is to define this definition, the DLV or DLUV, whatever we define carefully, in such a way that you can combine the sub problems to get bigger sub problem like using this head. So, this is exactly where the hard part of dynamic programming lies. Once you have defined it such a way that you can combine the sub problems to get answer to the bigger sub problem, then this thing is not that complicated. What do we do? Just like in the case of Belmont-Ford, we again look at a table. In this table, we have listed out all our vertices in one side in the column A, B, C, D, E, F, G, H, G, and again on the row. And basically, we will maintain this column at every level. So, at level I or level L, this one will contain say the length of the shortest path from B to C using 2 to the power L number of steps. Now, I cannot draw it here, but you can think of it as a 3-dimensional matrix in some sense, or a layer of matrices are there. For every L, I will have a matrix such that from the L minus 1th matrix, I can obtain the Lth matrix, and we keep on updating it. Here, say in the first step, what is the D0 UV, I just have added the edge weights as we have defined. This is the initialization part. Now, from these things, we can get the distance of say D1. How can we get? Say for edge E, I am asking now what is the shortest path of length 2 from G to E. Now, how can we do it? One obvious way is that let us look at the shortest path of length G to some other vertex. G to E is 9, but G to E I cannot do anything better than that, or I can go to G to F, which is 11, and then I can look at the path from, so this one, and from F to G using one step. So, F to E rather is minus 8. So, combining these two, I can get that the path from G to E using 2 steps is 11 plus minus 8 is 3. This way I can define D1, the length, the shortest path of length from any two, between any two vertices using 2 to the power 1, which is 2 edges. And again similarly, I can do this thing for D2 and D3 and D4, and we keep on doing it till how long? This is where the beautiful catch is. How long do we need to go? How many t to the power I do we need to go? Note that if I go, I am going for dk steps, this means that, say if I have the answer of dk, it means I know the shortest path of length between any two vertices of length 2 to the power k. Now, we know that in a graph, the shortest length between any two vertex cannot be more than size of the vertex set or size of V. So, all we need to do is go up to log to the base 2 of the number of vertices. So, if I can go up to d log V level, I will get the answer. So, basically the pseudocode is this, exactly this, and we just keep on updating this table to this DUV up till log V number of steps, because when you leave log V number of steps, by definition of DIUV, it is the shortest path of U to V in less than or equal to 2 to the power log V or V number of steps, and that will be perfect for us. So, correctness as exactly we defined, to go from vertex between two vertices of length 2 to the power L, you can go for length L minus 1 to 2 to the power L minus 1 to another intermediate vertex, and from intermediate vertex to length V using again 2 to the power L minus 1 steps. The runtime, note that we had the table contained V square number of entries, we maintain it for log v number of steps. So, we had a v square log v number of entries, and now for each entry, to update each entry, since I was taking a minimum over all u, so I required v steps. So, basically in this case, say this is for all u v, so it is a log v here. For all u v, there is a v square here, and this updating here minimum over this. So, this takes order v steps here. So, multiplying all of them is order v cube log v. Note that this thing works for negative edges also. So, in other words, to find the all pair shortest path for positive edge weights, we have the Dijkstra's algorithm that gives us the all pair shortest path in order v cube step. For Bellman-Ford gives us the all pair shortest path even when they are negative edge weights using v to the power 4, and this algorithm what is known as the repeated squaring algorithm. This one takes order v cube log v number of steps. Of course, the question is that can you do better? Can we do for negative edge weights, can you do say order v cube number of steps? And answer is yes, we can get v cube number of steps for all pair shortest path with negative weights. It is again another dynamic programming where we define the definition or have the definition defined very carefully, so that it will work out. So, today we looked at the all pair shortest path problem, and we looked at this another dynamic algorithm for solving the all pair shortest path, namely the repeated squaring algorithm. In the next few lectures, we will do more of dynamic programming.